Hi everyone, welcome in to the last video of topic 2. Right, so we are going over Maclaurin and Taylor series, but really we only need to talk about Taylor series, and I'll explain why. So we'll write down Taylor series. Now, the reason why we only want to talk about Taylor series is because Maclaurin series, see if I can spell this right, is a Taylor series. It's just a special case, and we'll discuss what that special case is. But essentially, if we talk about Taylor series, Maclaurin series is just one very special case of Taylor series. It actually makes it easier than a typical Taylor series. Right, so the equation that we're going to need to know what a Taylor series looks like is the sum from n equals 0 to infinity, so we have an infinite series again. And then we have f in parentheses n, we'll talk about what this means, evaluated at a. And a has to be given to you. So we'll talk about all of this notation. F raised to n, we'll talk about that notation, n factorial times x minus a raised to the n. Okay, there's a lot going on here. Okay, so first, let's talk about this notation. All right, what does f raised to n mean? And this is just saying the nth derivative, let me move out of the way, derivative of f. All right, so you can imagine if I plug a 0 in, right, well, that's the 0 derivative, that's just the starting function. If I plug in 1, that's the first derivative. If I plug in 2, second derivative, etc., right, of f. Right, so that takes care of that. Now we're evaluating the derivative function at a, right? And a is given to you. A is where, right, so a, we'll just put, this is given, but this is the center of your function, right, where you're centered. Right, and this will be given to you in the problem, right? It'll tell you you're centered at this value, right? This would be your A. And the reason why Maclaurin series is an easier version of Taylor series, right? It is a Taylor series, but Maclaurin series is just when your center, or A, is equal to 0, right? This is Maclaurin series. So it just simplifies this, right? So think about if we plug in 0 now for a, what does our equation become? So we'll put a little line here. So Maclaurin series just has the, right, it just looks as such. This is a 0, n equals 0, sorry, to infinity. F, right, the nth derivative evaluated at 0 over n factorial. And then if I plug in a 0 here, this simplifies to x to the n, right? So it actually looks nicer. Okay, I'll box this in. So this is Maclaurin, right? But again, they're exactly the same. The only difference is I've just plugged in a 0 for a. Right, so let's go ahead. We're going to do a Maclaurin series, but again, they're identical. Right, so I'll say let's find Maclaurin, and hopefully I'm spelling that right, or else I've spelled it wrong 3 times, series of f of x equals e to the 5x at x equals 0, right? Right, this is our center. Okay. And so what's tricky here, right? These two things don't change, right? The n factorial and the x to the n are already done. All we're looking for is what is the pattern here, right? What is the pattern here with the derivative? right? So let's write down a few derivatives as it does in your homework, and we're trying to figure out just the pattern of what's occurring here. So imagine, right, if we just plug in 0 to this function, right? So let's say f of 0, right? Because this is, when we plug in 0, this is the 0th derivative, right? We haven't taken the derivative. What do we get? Well, this will be e to the 0, which is 1. Okay, what about f prime of 0? Well, first, right, in your homework, the reason why it has you do this is you first find the derivative. So maybe we'll write out the derivative over here. The derivative is f prime of x, right? This is just a chain rule. 5e to the 5x. So now we have 5. We repeat the process again, right? I want f double prime of 0, which means I need the second derivative of x, which is going to be 25e to the 5x. If I plug in 0, I'll get 25, and I'm going to write it this way. This is 5 squared. So maybe we're starting to see what's happening here, right? If I take the 0th derivative, right, I get 5 to the 0. If I take the first derivative, I get 5 to the first. If I take the second derivative, I get 5 to the second. You can imagine what's going to happen here. Let's say the third derivative. We normally don't put 3 dashes. We'll just put it as such. What do we think we're going to equal? Let's double check, right? The third derivative with respect to x will be 125 e to the 5x. And now if we evaluate that at 0, right, what happens? I just get 125 or 5 cubed, right? So the whole idea here is, right, we're just looking for this pattern and we're good to go, right? So what is the pattern here? Well, the pattern is just 5 cubed, right? So we can write this out to the side. So our sum will take on the form of n is equal to 0 to infinity. We have our pattern, right? It's just 5 raised to n. Times x to the n all over n factorial. Okay, so we have our first part of our problem. I've run out of room. So we're going to need to continue on here. We're going to take a short break because I'll have to erase the board. But, right, we found our pattern for our nth derivative. It's just 5 raised to the n, right? Now, what are we going to have to do? What did I say? Anytime we have a factorial, what kind of test are we going to have to do? You are correct. You all guessed it. The ratio test, right? Because now it's going to want the interval of convergence and the radius of convergence. So we're going to need to do the interval test. So when we come back, I'll rewrite this over here. We'll do the radius of convergence and interval of convergence. We'll do one quick Taylor polynomial as well, and then we will be good. So I will see you shortly. Okay, we are back, right? We solved for what the Maclaurin series was, and now we can take this and find the radius of convergence, right? So I'll abbreviate radius of convergence and interval of convergence, right? Using the ratio test, right? The dead giveaway here is this factorial. As soon as we see the factorial, we want to use the ratio test, right? So the ratio test is the limit as n goes to infinity of a sub n, right? As a reminder, a sub n plus 1, all divided by a sub n. And this is going to give us some limits, right? And we'll go back over what the limit means once we solve for it. Okay, so let's just fill in the blanks. We have the limit as n goes to infinity of a sub n. So we have 5 to the n plus 1, x to the n plus 1, all over n plus 1 factorial. And now we can divide by a sub n, right? And we're going to get another fraction, so we'll end up with a weird 4-layered fraction. Or we can just multiply by the reciprocal of a sub n. So n factorial will be up here, and we'll have 5 to the n, x to the n. And hopefully, right, we've done one of these before. We know what's going to cancel out. I'll write some notes in case we forgot, right? We know that n plus 1 factorial is equal to n plus 1 times n factorial. So that's a nice cancellation here, right? And we also know, just as a reminder, 5 to the n plus 1 is equal to 5 to the n times 5. Right, so we have a bunch of stuff that's going to cancel out. Right, let's see what happens here. Okay, so again, this n factorial is going to cancel out, right, with everything except leaving the n plus 1. This will stay, right? So absolute value, we have an n plus 1 down here, right? Everything else with the factorials will cancel out. And again, 5 to the n times 5, 5 to the n will cancel out. We'll just be left with the 5. And same thing, right? Same rule that we applied down here. X to the n's will cancel out. We'll be left with an x. Okay? And at this point, you're fine to kind of complete the problem. However, I'm going to take it a step further. Right? The x's have nothing to do with this limit at all. So we'll put the 5x out here. Right? Limit as n goes to infinity of 1 over n plus 1. We know this is going to go to 0, right? So this will be equal to 5x times 0, right? Which is just going to be 0, right? So this is going to be a nice problem for radius of convergence and interval, because remember what this is telling us. This is saying for any x value that I plug in, any x value between negative infinity to positive infinity, I am always going to have a limit here of 0. Right? Always going to have a limit of 0. The x value here does not matter what it is. And so now we need to remember, well, what does this mean if I have a limit of 0? And the rule is, if L is less than 1, we converge, right? And so in our case, L is always less than 1, so we will always converge, which means our interval of convergence is negative infinity to positive infinity, and our radius of convergence is half of our interval, right? So just going to be infinity. Okay, this takes us to the end of this example. I want to do one with Taylor polynomials. Not going to be as difficult, essentially just a lot of tedious work writing out a Taylor polynomial degree 4. We'll do one example of that, and we will call it a day. See you guys in the next one. Last example here, dealing with Taylor polynomials. And so what I want us to find for this last example is, we're going to denote it as, let's use a different color, as T sub 4, which is going to be a Taylor, right, polynomial of degree 4. I'll just put degree 4. All right, so that's what this is standing for. I'll move out of the way. And I'm going to give us a function, right? And also, I need to tell us, because we're a Taylor polynomial, this is not a Maclaurin series, right? This is a Taylor polynomial from a Taylor series. This is not going to be centered at 0 anymore. So let's say 5 sine of x. And we'll say we're going to be centered at x is equal to negative pi over 6. Okay, so we need to remind ourselves of a few things, and I'm going to write it out over here. What does a Taylor series, right, look like? Well, it looks as such from 0, let's say n is equal to 0, to infinity, right, of the nth derivative evaluated at our center, which in this case is negative pi over 6, divided by n factorial times x minus our center to the n. Right, so we just need to go through each piece here, right? So first we're just going to plug in 0, right? We need the 0th derivative. We plug in 0 factorial, which is equal to 1, by the way, and it's going to be to the 0th power. Okay, so let's see what happens. The 0th derivative is just the function, right? So now all I need to do is evaluate it at negative pi over 6. Right, and I'm going to rewrite this. This is also equal to what? Negative pi over 6 is the same as 11 pi over 6, just so we know. Okay, so we will say f, right, the 0th derivative, so f of negative pi over 6, again, which is pi over 6, or which is 11 pi over 6, but I'll leave it, is equal to 5 sine, and I know this is dumb, but just I'm going to use the other one because it's easier to evaluate, 11 pi over 6. I should have just wrote it here. Okay, so that's our first step. We need to remind ourselves of the trig circle. Think about sine as our y values, right? So 11 pi over 6 puts us in the 4th quadrant. We're going to have, right, negative y values in the 4th quadrant. The reference angle here is pi over 6, right? So our sine value is going to be 1/2. Right, so this ends up being 5 times 1/2, or 5 over 2. Right, so our very first thing says, right, if I plug in the 0, I get 5 over 2 divided by 0 factorial. I'm going to write it all out, even though, right, we know what 0 factorial is. And this is x minus a, so x plus pi over 6, but it's to the 0 power, and what do we know about that? Anything to the 0 power is going to be correct, right? So this is going to be 1, this is going to be 1. We end up with just a 5 over 2, and I'm just going to write it going forward. All right, so now what's my next step? Right, plus, I'm going to do the third, I'm going to do 2 degrees. So I'll have you guys do the rest. Right, my next step, let's see, let's just start plugging in everything. Well, I need to do this derivative of sine. Right, and the derivative of sine is what? Cosine, perfect. Right, so we have 5 cosine of 11 pi over 6. Right, that's our derivative, that's the first derivative, over 1 factorial, and now it's x plus pi over 6 to the first. Okay, cosine of 11 pi over 6, we're in positive x territory. Our reference angle is pi over 6, right? So we have a rad 3 over 2. 1 factorial is going to be 1, so we're going to end up with 5 times, this is rad 3 over 2 times x plus pi over 6. We can leave it just like that. Okay, what's our next one? Right now we need the second derivative. Well, we have the first derivative. Now we need the derivative of cosine, which is negative sine. So now we have minus 5, right, because cosine is negative sine, sine 11 pi over 6 all over 2 factorial, right, times x plus pi over 6 squared, right? So I'm going to only go up to 2 degrees. I believe the homework, I know I said 4 degrees, I lied because I ran out of space, but hopefully we're understanding the pattern, right? We're just taking derivatives and plugging in values, right? So if we know our derivative, in this case of sine and cosine, we should be fine. Let's go ahead. Again, sine of 11 pi over 6, we already evaluated it, right? It's going to be negative, what happened here? Should this have been a negative 1/2? This should have been a negative 1/2, right? Sine of 11 pi over 6, fourth quadrant, negative y's. This should have been a negative sign. Anyone catch it? Hopefully you did. So negative here, negative here. Sorry, guys. Having to double check. Yeah. Now in this case, though, sine of 11 pi over 6 again, negative 1/2, but, right, we have a negative sign here, so it ends up being a positive 1/2. So now we end up going back to positive, or staying positive, right? Negative 1/2 times a positive, or times another negative. So we have 5 over 2. So 5 over 2, it's a weird 5, coming from this piece here. And then another 2 factorial, right? 2 factorial is just 2, 2 times 1. So you guys can simplify that. And then, of course, x plus pi over 6 squared. And I don't believe you have to square these out in your homework, right? You can keep going and just leave it as such. So again, simplify this to 4, right? Obviously 2 times 2 is 4. And I think for your homework it wants degree 4. So you have a couple more to do, but hopefully we see the pattern, right? The main thing is, right, knowing our Taylor series, and now we're just expanding it out, right? We just want the first 4 terms. So you take the 0th derivative, right? We're plugging in 0. In this case, we're just evaluating the function at 11 pi over 6, right? We get the negative 1/2. We simplify, and then we take our first derivative. We got a positive cosine. We plug in the 11 pi over 6. We have a positive, right, rad 3 over 2. And we keep going. Now we have 2 derivatives. We want our third one. It's going to look all squeezed in. So I'll give it to you guys, right? We can talk about it here. What's the derivative of a negative sign? You'll have a negative cosine, right? You'll plug in the 11 pi over 6. You'll have 3 factorial. This will be cubed, right? It's just the same thing repetitively. So hopefully this helped with those 2 examples. Again, for those watching from GCU, 26 and 27, right? We saw the announcement. Okay, sounds good. I will see you guys in class.